Before starting the design of a control structure, it is necessary to have some knowledge of the process. Well, first of all, you have to understand the underlying dynamics in the time domain, but also in the frequency domain. If you know the process in the frequency domain, it's a bonus. This is what we mean by process behavior knowledge. This section will review the main building blocks and will enable you to identify the process dynamics from its signature in the time domain, for example a step response, or from its signature in the frequency domain, for example a frequency response. Of course, process knowledge is much more than just knowing the process behavior. It is always a very good idea to understand, between quotes, the process and to have some insights behind the physics of the process, so that you, for instance, know how the process is interacting with other processes. To decide on the control structure, it is a good idea to have some awareness of the linearity of the process, the presence of disturbances, load disturbances, output disturbances, are these disturbances measured or not, and finally to have an idea of all the constraints that are imposed on the system. You will often see that a good discussion with the process engineer or with the operators will help you to acquire quite some process knowledge. The process has huge impact on process control. Well, first of all, on the control structure, as we will see in the next section. Let us take, for example, disturbances. Well, they have a serious impact on the controller structure. If you have, for instance, a load disturbance, well, cascade control can help you reject it if this cascade can be implemented. And for instance, if you have a disturbance on the output, well, then feed forward can be used. Of course, this disturbance needs to be measured. The process behavior, that is the underlying dynamics, has an impact on the controller type. If the dynamics of the process is first order, of course a PI controller is sufficient. But for instance, if you have a process with a substantial second time constant, well, then PID control can be interesting. Also, if there is a large dead time in the system with respect to the main time constant, well, then more complex control structure can be used, such as the Smith predictor or internal model control. The type of control problem, so disturbance rejection or tracking, this is also a form of process knowledge, has influence on the aggressiveness of the controller. So for instance, the controller will be more aggressive in a disturbance rejection case. If the process is nonlinear, you might have to adapt the controller tuning in function of the working point. This will lead to gain scheduling or simply scheduling. At the end of the course, you should be able to select the appropriate controller structure, the appropriate controller type, given your knowledge of the process. This means that at the end of the course, and especially at the time of the exam, you must have a mental picture of all the available controller structures and controller types with their associated area of application. We'll start this section on process behavior with a very important but rather simple concept, the concept of the process gain. Right? In order to obtain this process gain, what is usually done is to apply or impose a step at the input. Okay, and the input is mv, the manipulated value. So the increase will be delta mv over here. So what you're going to do is observe the response of the system, and of course, since the system is almost always dynamical, well, you'll have a response that could be this one. Well, the idea of a gain is really the ratio in steady state. So this means that the transients have disappeared because the system is dynamic. Well, after a while the transients will disappear and you'll have, after settling, a delta PV, right? And the process gain is really the ratio between this steady state increased delta PV over the delta MV that has been imposed, and will denote this gain as Kp, right? Kp as units, it's the units of PV divided by the units of NV. Note that the LTR 700 system and TC Lab have different process gains. For the LTR 700 system, the gain has units percentage of the temperature output scale over percentage heating power, and TC Lab has process gain degree Celsius over percentage heating power. We have seen for the LTR 700 system that the process is non-linear. So if you do a 10% heating power change around a different operating point, for example, a change from 50 to 60% or a change from 60% to 70%, well, then the resulting steady state delta PV is different. This means that the process gain is operating point dependent. Well, the next type of process behavior that we tackle is process delay or dead time. So here you have an example of a transporter belt or conveyor belt, and there is transport of material between point 1 and point 2. So W1 and W2 here are linked simply by this relation over here, right? There is a delay in between W and W1. This delay can simply be computed over here. Well, it's the distance that has to be covered, and this is in meters, of course, divided by speed, and of course this leads to a delay, and of course it has units seconds, right? You can see here that this delay is throughput dependent, so it depends on the speed of the conveyor belt. Here you can see things visually. W2 is a delayed version of W1. You can clearly see that there is no amplification or attenuation, right? There is just a phase shift. Well, as we have seen, dead time is throughput dependent. It depends on speed, but it can also depend on a flow. Causes are transport. I've already talked about the transport of material in the conveyor belt, but also a bad location of the measurement can introduce delay. For instance, a sensor can add delay, and of course when you're sampling the system there is a delay that is due to the zero order hold mechanism. In this course here we'll assume that TS is sufficiently small that this zero order hold mechanism has very little influence. The succession of several time constants has also the effect of a dead time. We speak of an apparent dead time. So let us have a look at that. We take several first order systems in series. So let's just take 3. And we will look at the step response, right? So at the input we apply a step, and then we're going to have a look at this step response. We can have a look at the output here of the first order system. So the response will look like this. So this is the typical response of a first order system. At the output of the second first order system, it will look like this. This is the response of a second order system. And at the output of the third first order system, it will look like this, right? So you can see that the succession of several first order systems introduces kind of a delay over here. We speak of an apparent dead time. The process delay plays an important role in the optimization of the controller. If the process delay theta becomes large with respect to the main time constant of the process, so if this quantity increases, it becomes more and more challenging to optimize the controller, or the PID controller in our case. If theta becomes, well, much larger than 2 times the main time constant, it becomes, well, almost impossible to use a PID controller, and then you'll have to use other control strategies such as the Smith predictor or the internal model control. These concepts, these control strategies are not part of this 15-hour course, but if you're interested, you can refer to the course Practical Process Control, which is available online. We have seen in the example of the conveyor belt, and we will see next, that dead time introduces a phase shift. So dead time will have a tendency to decrease the phase margin, and so it will have a destabilizing effect. There's an example that you can use to easily explain that a dead time as a destabilizing effect. So it's the example of the shower in a camping, and this is the shower spray hose, and you have of course 2 knobs that you can use to control the temperature of the water. And then in a camping, what is usually happening is that you have a boiler, right, that is situated very far away, and we speak of more than 100 meters, right? So if you're in the shower and you act as an aggressive controller, what you will do is, well, kind of ask for a flow of warm water, but since you're located so far from the boiler, nothing will happen for a while. And what you'll do is, well, turn this one open to 100%. Then after a while, of course, what will happen is that the warm water is there, and then you get burnt. So what you do is close this one to 0% and, well, start opening this one. And then of course, after some delay, what happens is that the water gets very cold, right? So this is typically what happens if you use an aggressive controller on a process with a dead time that is large with respect to the time constants. You will see oscillation in the system. Well, a delay in the time domain is really PV is equal to mv t minus theta, and if you go to the Laplace domain, right, this is what you obtain. Remember, to have an idea of the frequency response, what we need to do is take P of S, evaluate it at S is equal to j omega, and then take the module. So this is the module of P of j omega, and this will be used in the top part of the Bode diagram, and then you need the argument of P of j omega. In our case here, the process P of S is simply exponential of minus ts. So if we replace this by s is equal to j omega, this is what we obtain, right? Exponential of minus theta, I'll put the j in front, theta omega. And this here is in polar form, so you can clearly see that in this case we have a 1 over here, so the magnitude is 1, and the argument can simply be read, it's minus omega theta. Okay, so there is no need to do a calculation like this because this is obvious, right? You simply take the transfer function, replace s by j omega, and you can immediately see that the module of the gain is 1 and the argument is minus omega theta. Observe that in the previous formula the phase is expressed in radians. This is important. Well, this is the frequency response for this process delay or dead time. We had seen that the module was 1, right? And the argument of p of j omega is simply minus omega theta, right? So you can see here that there is no influence of frequency, and if you use dBs, of course, you have here that the magnitude plot in the Bode plot is equally 0 at all frequencies, right? Here we see that the phase shift is increasing with frequency, so we have a linear dependence on omega, but remember here that we have here the log frequencies, so we can see here that we have this exponential behavior. Okay, you can see that you have a phase shift of 1 radian where omega theta is equal to 1, right? So this is 1 radian and this is approximately 57 degrees, right? So where omega is 1 over theta, we have a phase shift of 57 degrees. That's 1 radian. Here we have theta is equal to 1. 1 over theta is therefore at 1 radian per second, and we can see that indeed here we have a phase shift of minus 57 degrees, which is, and this is approximate here, and this is 1 radian. Well, we have seen in the previous section that an integrating process can be described by a transfer function h of s with an s at the denominator, and we'll give it here a gain kp. Here we have an output flow, but assume here now first that there is no output, that there is just an input flow, right? And this is mv, right? What you can do is take an mv that is positive and look at the output level, right? And you will see that the level is increasing, right? So that you have will kp mv t at the output. So if you can compute the slope, we will call this the slope, right? Well, then kp can be determined simply by taking the slope that you observe and divide it by mv, right? Here the situation is a little bit different. We have an output flow, right? And we will assume that it is unknown, right? And what we'll do is do a manipulated value change. So we'll start with an mv, and apparently this mv is such that the output flow is larger than the input flow. As you can see, the level is decreasing, and after our step we can see now that the level is increasing, and this is telling us simply that now in this second situation, well, the input flow is larger than the output flow. In this slide we have the same situation as before, but we have added a delay, and as you can see, the delay can really be determined rather easily. You can see that after we have had the change of mv, well, it takes a delay of theta before you can observe the change of slope. So remember that we have a process here that is integrating. It will have gain kp, and it is an integrating process, right? And what we want to do is to determine kp, and we have done this experiment on this, well, integrating process where we had this unknown output flow, and we want to determine kp. So what you need to do is to compute the slopes before this the manipulated value change and after. How do you compute the slope? Well, you set a set period delta t1 and you look at the change in delta pv, right? So slope 1 is delta pv1 over delta t1. You do something similar to compute the slope after the manipulated value change, and you'll obtain this slope 2 and slope 1 experimentally. We have here our process in the Laplace domain, and it's kp over s, right? And in the time domain you can write it like this. Note that for such a process, if mv is equal to 0, when then pv is constant, right? If mv is positive, then pv will be growing linearly, right? And if it's negative, pv will be decreasing, right? Here we have a constant mv, so the output will be kp times this constant time t, right? So what we see over here is the slope, right? And we have determined this slope experimentally, and what you see over here is the slope for the second operating point mv2, and we have also determined this slope experimentally as follows. So we have here that kp mv1 is this slope that we have determined experimentally, and we have something similar for kp mv2. If we subtract both equations, this is what you obtain, and you can see here now that you can obtain kp experimentally from this experiment that is shown in the previous slide, and this is done independently of f out. Of course, f out has to be constant. Assuming that we are working in a normalized fashion and that we are at steady state, we can write pvn, and for normalized is kpn mvn times t. We'll assume that mvn is constant, right? It is expressed in percent. We are at steady state, so the output will grow linearly. The output is also expressed in percent since it is normalized, and you can see here that this is growing. This has, well, units time, so this one must have units 1 over seconds, right? So this is why kp is often written as 1 over a time constant, when kp is, well, the gain of an integrator, and this will be the case in the section on PID control. Well, the integral action, right, will be 1 over ti, the integral of the control error, right? And you can see here that the gain of the integral action has been written as 1 over a time constant. Well, we have just seen how we can obtain the gain of the integrating process experimentally, but very often you do not need to do experimenting. For instance, the level of the tank is linked to the input flow by integrating system, and the gain is 1 over the section of the tank. For instance, the voltage on a capacitor is linked to the current by an integrating process, and the gain is 1 over the capacity, right? And you could add, for instance, that the current through an inductor is linked to the voltage by an integrating process, and the gain is 1 over the inductance. Coming back to this example of the level in a tank, if the tank is lying on its side, then things look like this, right? And the relation between the level and the input flow, F in, well, becomes non-linearly, because you can see here that depending on the height, depending on the level in the tank, this tank section will vary. So we have a non-linear behavior, and according to the working point, the dynamic behavior will be different. The working point will be determined here by the level in the tank, and you'll have something very similar if you have a, well, conical tank. So for instance, in this region over here below this line, well, the level, the relation between level and input flow will be non-linear, as the section is changing all the time. When you're above this line, of course, things become linear again, and then you have the standard integrating process again. We can now have a look at the frequency response of this integrating system. Remember that we have to take P of S, evaluate at S is equal to j omega, and then take the module and the argument. In our case, we'll have Kp over j omega. The module will be Kp over omega, and the argument of P of j omega, because of this 1 over j here, is minus 90 degrees, and this is clearly observed here in the phase Bode diagram, right? So now we have to look at the module. You can see that this module is evolving as 1 over omega, but in a log frequency Bode plot, this looks like it is evolving linearly, right? And the slope here is minus 20 dB per decade. Where is this coming from? Well, we are working in dB, so what we have to do is to take 20 log 10, and what I'll do is look at what happens when I multiply the frequency by 10. So we'll have Kp divided by 10 times omega, and we'll use this formula that log of A times B is the log of A plus the log of B, and this is true in any base, so also in base 10. What we'll have here is 20 log 10 of Kp over omega. So this will be the gain here at the frequency omega expressed in dB, and here you'll have plus 20 log 10 of 1 over 10, right? So this one will be minus 1 times 20, so this is minus 20 dB. So what you have to do to obtain the gain expressed in dB at 10 times omega, well, you have to take the value in omega and will decrease this value by minus 20 dB. So indeed here you have a slope of minus 20 dBs per decade. Well, another important fact is that you can determine the gain by just looking at this Bode diagram. The frequency at which Kp omega is equal to 1 is, of course, omega is equal to 1 over Kp, right? In our case, Kp is equal to 1, so the frequency at which we'll have a gain of 1, which corresponds to 0 dB, is indeed here at the frequency of 1 radians per second. This is more intuitive than you think. If you take an integrating process, 1 over s, and at the input you apply cosine omega 0 t, assuming that you're at steady state, what will come out here, if you integrate this cosine, is the sine of omega 0 t divided by omega 0, right? And the sine is really a cosine that has been shifted by minus 90 degrees. So this is what you see over here. The gain is 1 over omega 0. The smaller the frequency, the higher the gain. And this is also what you see here in this Bode diagram. Let us look at the following loop. So we have an integrator, Kp over s, and this very simple loop with a minus and a plus over here, right? And we'll put a 5 at the input over here, and we'll ask the question, what are the values in steady state? Well, the only steady state that is possible is to have a 0 over here. If we have something positive, it will be integrated and it will evolve, so it's not steady state anymore. So if we have a 0 over here, it means that we have a 5 and a 5 over here. So here you can clearly see that in steady state the gain is infinite, and this is indeed what you see here in the Bode diagram. And when you encounter a process where you have an input that is 0 and an output that is finite and non-zero, well, this means that there is an integrator in this process to cause this effect, and this integrator will cause an infinite static gain.